Okay, hi everybody. Part A, the geometric sequence. Please define it recursively and by a formula. Well, in the previous problem, we know that if you choose any complex number A and another complex number R, then the formula is that the nth term of the sequence is just A times R to the n. Okay, and this gave like the sequence AR, AR squared, AR to the third, AR to the fourth, etc. So this is the formula. This I would say is like an explicit formula for the nth term x sub n of a sequence. Okay. Now, what is recursive? Recursive definitions, well, what do they do? So recursive define the sequence x sub n for, I don't know, for n in the natural numbers maybe, or the natural numbers with 0, or maybe you could write the integers that are greater than or equal to 0, or maybe you want to start at 1, so you say greater. Anyway, whatever. So you're defining this sequence by listing infinitely many equations in the infinitely many unknown x sub n. Okay, so I mean, it's best by an example. So let's use this example. How do I give this as an infinite list of equations? I want to define the n plus 1th term in terms of the x sub nth term, but how? Well, how are they related? Well, I start at A, I go to A to R, AR squared, AR to the third, and you see that each next thing is multiply by R, multiply by R, multiply by R. So here's the formula. X sub n plus 1 is equal to R times x sub n for every n, whatever we're doing for the sequence. Wherever we start the sequence, whether we started at 0 or 1 or 2 or whatever. So, okay, so this is infinitely many equations. There's also, in order to solve this list of equations, you have to say sort of what the first thing is doing. So I'm going to then say x sub 0, or maybe else, yeah, x sub 0 is A. Here, infinite equations in infinite variables or unknowns x sub n. Okay, so this is a lot like, let me just go as to help you understand the difference here between this formula, which is not recursive, and this formula, which is recursive. Well, it's not a formula, it's just a list of equations. Infinitely many. Okay, so the difference is sort of like how a circle can be described as x squared plus y squared equals 1. All the xy that satisfy this equation. Okay, that is like a recursive, it's sort of like recursive, but really people will call this implicit. Because you're not really explicitly saying what are the points on the circle. What are they? Whereas if I say cos theta comma sine theta for every theta in 0 to 2 pi, a subset of the real numbers, this is explicit. So this is like, anyway, so here's explicit formula for many, infinitely many points on the circle. This is like the explicit formula for all the infinitely many terms of a sequence. This is an implicit expression. It doesn't actually give you any of the points. It just tells you an equation that they have to satisfy. And that's like the recursive definition. Okay. So we call this parametric and this implicit. And in the world of sequences, it's sort of like an explicit formula or a recursive definition. Okay, that's part A. Obviously, you don't need to include this this sort of analogy. This was just to help you understand. Okay. So I gave the formula and the recursive definition for geometric. Now let's define the factorial sequence recursively and explicitly. So first, I just have to remember, what is the factorial sequence? I don't know, 1, 2, 3. So 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial, dot, dot, dot. In other words, 1, 2, 6, 24, 120, dot, dot, dot. And explicitly, x sub n is just n factorial. Okay, so this is the explicit formula. And then what about the implicit, i.e. Also called recursive definition? Well, that will be the next term, n plus 1, is something times the old term. What is it? It is n plus 1 times the old term. Let's make sure that works. x5 should be 5 times x4. And that is 5 times 4 factorial. And that is, in fact, 5 factorial. So that works. This works so far. Now to get it started, x sub 1 is 1. Okay, there we go. That's it. Okay. Is that it? Okay, define the Fibonacci sequence recursively. Okay, so Fibonacci. First I have to remember what this is. This is just a good example to know. It's a sequence that goes 1, 1, 2, 3, 5, 8. Okay, I'll stop after. We don't want to do 3 digits. That's too much. So you just add the previous 2. But that means that the n plus 2th term is just the xn plus 1th plus the xnth. Another way to write this exact equation would be xn equals xn minus 1 plus xn minus 2. These are actually the same list of equations if I say for n in the set, what? I guess it has to start 1, 2, 3, 4. So I guess I could say n in z greater than 0. And then here I would say for n in the set. Now we want to start at x1. Well, we can start wherever we want, but I guess I would just say this starts at 3, 4, 5. So I could say n in the set of integers that are greater than 2. Okay. Just so that this is x1 in the lowest case. And then I have to actually get started. I have to say that x1 is 1 and x2 is 1. So this would work right here. Okay. You could also use this instead of this. But you see this is infinitely many equations in infinitely many unknown variables x sub n. Okay. That's it. It just said recursively. Now this one, I'm actually going to put this on your homework. I'm going to make you try to figure this out. Fibonacci is easier to do by just giving you infinitely many equations. It's much harder to see that this is actually an explicit formula. In other words, the nth term should be this. You could also say x sub n equals this. Yeah. For n in the integers greater than 0. This is not obvious that this is true, so this will be your homework.